Hey, good morning! Chemistry coach coming at you again. You ready for another weird concentration unit? Molality. We're not even covering them all. There's some specific for biochemistry. I remember was there an osmolarity or something? There's some crazy ones out there, but they're specific for different industries, right? So molarity is the one we're used to in academics, but when I was working out in industry, we didn't use molarity. We used a lot of percent units and things like that, mass percents, right? These relative concentration units. All right. So molality has very specific applications and an extreme advantage over all of these other units we've been using, right? Molarity, normality, moles per liter, equivalents per liter, yada, yada, yada. So it's a special concentration unit. And what's different about this one is all the other ones had the amount of solute, some solute, over the amount of some solution, right? Molality is different where it doesn't have any solution terms. It is the solute-solvent amount ratio, right? Now, what are these amount terms? It would be molality, which has this little kind of italicized letter M for molality. So many things start with M in chemistry. You got capital M for mega and weird M for molarity, and this is nuts. But it'll be the moles of solute. So the term used for the amount of solute would be moles. That's the molality. But the solvent term in the denominator is kilograms. So it's mass of solvent in kilograms. That's very different. What's different about this one, this does not have any volume units or solution terms. Whoa! So we're going to be using this unit specifically for a couple of colligative properties we're going to look at later for solution properties. Looking at freezing. So how does a freezing point or a boiling point change from a pure solvent when you add some solute to it? How does that change some of the properties of the solution, and can we calculate those? We'll be using molality terms for that. And here's a big reason for it. Look at molarity here. It's moles of solute per liter of solution. And remember from first semester of general chemistry or prep chemistry, thermal expansion. If you increase the temperature, you increase the volume. So as the temperature goes up on a molecular level, you've got increased vibrations and the volume increases. That's why density decreases. Density is mass over volume. So as the temperature goes up, you're dividing by a larger denominator. So density drops as temperature goes up. Well, the same thing is true with molarity or any other concentration units that has volume of solution in the bottom. Since molality has no volume terms, it's independent of temperature. Its value stays the same over any temperature range, right? Whereas molarity drops as the temperature increases. So if you make a solution at, say it's a colder day, 19 degrees Celsius, and you come in a week later in Southern California, we get a heat wave, it's 23.5 degrees Celsius. The concentration you thought it was is not what you're working with now because of the thermal expansion of your solution. You're like, darn, the molarity is actually lower than you think it is. So again, as temperature increases, volume increases, and if the volume increases in the denominator, the molarity is going to drop. In prep chemistry, the percent error, who cares, right? General chemistry, probably unless you're doing some really detailed analytical lab work, probably not a big deal to account for this in general chemistry. But if you're taking analytical chemistry as a junior or senior chemistry major, you might want to worry about the temperature effect, all right, causing changes in the solution concentration values. So beautiful thing there. And because we're dealing with later properties of solutions that are temperature dependent, it'd be nice to use a concentration term that was temperature independent, right? Where it didn't matter. So let's do an example problem of molality just to get you used to it, and we'll pull in some review from first semester general chemistry units as well. Let's do it. Get your calculator ready and your periodic table ready. Here's an example problem, right? And to pull some review from the first semester of general chemistry. Let's say you got some little bottle of vodka, and it's 40%. Usually, they're not worried about sig fig. So let's just say it's good to 3 significant digits. 40.0% by volume ethanol in water, right? Which means if you had 100 milliliters of vodka, you would have 40.0 milliliters of ethanol in it, all right? And I think if you double that, you get the proof, right? So I think vodka's 80 proof. So take the volume percent of the ethanol in some kind of spirit, double it, and you get the proof, right? So 100 proof would be 50% by volume of the ethanol in water, et cetera, et cetera. 180 proof would be 90%. Oh, burns, it burns. What's the molality of that 40% volume percent? See the VV, volume. That's not, if it was mass percent, this would be a totally different thing. That'd be grams over grams. This would be milliliters over milliliters. The density of ethanol, didn't specify temperature, right? 0.789 grams per milliliter. So we're assuming room temperature-ish in this. So if we have a 40.0% volume of vodka solution of ethanol and water, what is its molality? So tying some older first semester units of concentration to some newer second semester general chemistry units. Molality. All right. You could do this in 2 steps, really. You're not going to be able to do it all in 1 step, but I'm going to just break it up so you can see each component. And once you become more familiar, if you want to smash some of these steps together, go for it. Step number 1, we need to know how many, because remember, what's molality? It's moles of solvent, moles of solute, the ethanol, over the mass of solvent in kilograms. So the solvent being water, right? Which specifically is stated here. If we didn't state that, you would make that assumption. So let's figure out the moles of solute. If you don't know ethanol, CH3CH2OH. Okay, so you can get that from the definition, right? This would be 40.0 milliliters of ethanol per 100 milliliters of vodka by definition. Okay? That's our starting point. So you can convert that 40.0 milliliters of ethanol to grams of ethanol from the density to moles of ethanol using the molar mass. Boom! You've got the numerator of your molality. Hey, hey. Now we need kilograms. Excuse me, breakfast burp. Kilograms, well, we aren't given mass. We're given volume, which would be 100 milliliters of vodka. What do? We need the volume of the solvent. So again, some of these newer second semester general chemistry units, we need to extract the solvent information from the solution information. So how do we get the volume of the solvent? Well, if this means 40.0 milliliters of solute per 100 mils of solution, you should be able to subtract those to get the volume of the solvent, right? And once you have the volume of the solvent, go to step 3, figure out the mass of that solvent in kilograms. There's an issue. We want to go volume to mass. There was no density of water provided here, was there? So you're going to have to make an assumption about the density of water. Because I want you to try this on your own and see how you do. Well, once you've got the moles of the ethanol, the solute, right, and you've got the mass of the solvent in kilograms, just divide them, and you got the molality. See how you do, right? Couple assumptions in here on the densities. Did you get steps 1 and 2 done? All right, so step 1, we'll focus, and you can do this out of order. You don't have to do the solute first. You can do the solvent first. It's up to you. Doesn't really matter. So let's figure out how many moles of the solute we have, ethanol in this case. All right, well, let's look at the definition of the volume percent. This is the starting point, right? So if we have, volume percent is milliliters of solute over milliliters of solution, right? So if we have 40.0%, percent is parts per 100. So let's assume 100. You could assume any number you want, but I just assume 100 milliliters of the whole. Percent is part over whole and parts per 100, right? So if I have 100 milliliters of solution, that would mean I would have 40.0 milliliters of solute, right? 40.0 divided by 100 is 40.0%, right? So I make that assumption, you've got 100 mils. Go review the video on percent concentrations for this, right? From first semester. Well, our solute in this case is ethanol, and our solution is the vodka. The vodka is the mixture of the ethanol and water. So 40.0% by volume would be 40.0 milliliters of ethanol over 100 milliliters of vodka. That's the starting point. If you don't do that, then you don't know where to start, right? All right. So we want the solute, we want the moles. So we have 40.0 milliliters of ethanol, CH3CH2OH. Well, I want to go to moles, so I need to get to mass. Oh, yay, I gave you the density. Yay, yay, yay. So there are 0.789 grams of ethanol per milliliter, making an assumption on densities, right? So we don't know what temperature this is at. And that allows us to convert milliliters of ethanol to grams of ethanol. I didn't have room to write the ethanol in there. You could put like, if you want, you could put like ETH or something, some kind of shortcut notation for it. And then once we have grams, we can just divide by the molar mass. Grams on top, grams on bottom. That'll get us to moles. So we've got 2 carbons. So take, from my periodic table, 12.011 times 2. We've got 1, 2, 3, 4, 5, 6 hydrogens. So take 1.00794 times 6 and add the 1 oxygen at 15.9994. Looks like the carbon's going to limit us to 3 decimal places. So I get 46.06904 grams of ethanol per mole, good to 3 decimal places. So when we do all this multiplication division, limited by sig figs, I get 3 significant digits, an assumption we made from the start. 3 significant digits in the density and 5 significant digits in the molar mass. So we're limited to 3 significant digits. So I get 0.68505 moles of our solute ethanol. Yay, that's the numerator, right, of our molality, right? Now we just got to get the kilograms of the solvent. And we don't have any information on the solvent, do we? We have solute and solution. No! All right, here we go. The extra step involved. Step 2. We need to extract the volume. Extract. This is a symbol for extract. 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 One of those mornings. So I've got 6 kids running around this house, 4 cats, a dog, a bearded dragon, a conure. It's crazy in this house today, right? So let's extract. I'm going off on a rabbit hole here. How do we get the volume of the solvent, the water, from this? All right, well, we have the 2, right? Isn't the volume of the solution just the volume of the solute plus the solvent, since we only have 1 solute, right? Therefore, our solution is the vodka, our solute is the ethanol, our solvent is the water. We have specific. Sometimes you don't have a specific name for the solution like that. So if we want to isolate the volume of the solvent, just subtract the volume of the solute from both sides. So the volume of the solution minus the volume of the solute should be the volume of the solvent, right? So the volume of water will be the volume of the vodka minus the volume of the ethanol. Straightforward. You're just taking 100 milliliters minus 40.0 milliliters. The 100 milliliters is an exact value by definition. Right? We're making the assumption we have exactly 100 milliliters of vodka or solution, but the 40.0 is not. So we're going to be limited to the tenths place in the subtraction. So that leaves us 60.0 milliliters of solvent, water in this case. That should allow you to move on to step 3, where we can take that, convert that to kilograms, and then in step 4, just take the moles of the ethanol divided by the kilograms of the water. Do steps 3 and 4 for me. I'm out of room. Had to make an assumption in step 3, right? So we're taking that 60.0 milliliters of solvent, water, but we got to convert it to a mass, which means we need the density. That was not provided in the problem. We have the density of ethanol provided. I'm assuming most of us haven't memorized the density of ethanol, but you should know the density of water approximately, say, to 2 significant figures, right? So if the density of water is not provided, no temperature, no density, anything, we're going to have to make an assumption on the density of water or super dilute solutions. So I think 2 significant figures is probably fine in this case. You're pushing going to 3. 1.00 might be pushing it because you don't know the temperature, right? And the density decreases as temperature increases. So 1.0 grams of water per milliliter water is a fairly safe assumption. You can go to 2, right? A more accurate way of doing this is if we knew the temperature, we could look at tables of density versus temperature and do a linear interpolation. Or if we had a plot, we have y equals mx plus b from the least squares fit. We could actually calculate a pretty accurate density to 3 or 4 significant digits, a 0.9972 or something like that. But it's not going to make that huge of a difference for this particular problem. But if you're doing higher level analytical work, I wouldn't make that assumption. I would get a much more accurate density of water. Good? Get it? Got it? Good? Of course, we got to convert that to kilograms because the denominator of molality is kilograms of solvent. So if we take the 60.0 milliliters of water times the density of 1.0 grams per milliliter, we can get rid of volume and go to mass, convert grams to kilograms. That's exact. That's not exact. That assumed density is not exact. So we're going to be limited to probably 2 sig figs from this. So I get 0.060 kilograms of water. There's no non-rounded value there. We've got all the pieces to the puzzle now. We can go on to step 4 and calculate the molality of this vodka solution, which would be the moles of the solute over the kilograms of the solvent. So from step 1, 0.68505 moles of ethanol, good to 3 significant digits. Divide that by the mass of the solvent, the 0.060 kilograms of water we determined in step 3. We're doing a division, so we're limited by fewest sig figs. We got 3 sig figs in the numerator, 2 sig figs in the denominator, so our answer is limited to 2 significant digits. I get 11.41 moles of ethanol per kilogram of water. Good to 2 sig figs, so that is closer to 11 than to 12, so we'll round it to 11. So that'll be 11, and you can use, if you don't want to write the moles of ethanol over kilograms of water, you can just do the little cursive M, 11M. And the terminology in chemistry is that's 11 molal, kind of like if we had a 2.55, capital M would be a 2.55 molar solution, short for molarity. So we use molal solutions. This would be an 11. So vodka, 40% vodka solution by volume, or 80 proof, would be 11 molal. Hey. And we're going to use a lot of molality when we're doing some of these later colligative properties of solutions.